Hi, I'm Bryce Sandlin from the University of Waterloo, and our talk is called Space-Efficient Data Structures for Lattices. This is joint work with J. Ian Monroe, also from Waterloo, and Corwin Cinnamon from Princeton University. All right, so what is a lattice? A lattice is a partial order L in which the set of elements larger than any x, y, and L are all larger than or equal to an element x join y. Similarly, the set of elements smaller than any x, y, and L are all smaller than or equal to an element x meet y. So you can see here in our diagram on the right, if I have two elements x and y in the lattice, if I look at all elements that are above x and all elements that are above y, well, the elements that are in this intersection must all be above the join of x and y. And something similar holds down here for elements below x and y and the meet of x and y. Okay, so what are some examples of lattices? So on the left, I have the lattice of integer divisors of 60 ordered by divisibility. So as I ascend vertically, the numbers get larger, and there's a relation drawn when the lower element divides the higher element. This is kind of a cool lattice because if you take, say, like the elements 15 and 6, the well, I should say just the meet of any two elements in the lattice corresponds to the greatest common divisor of those two elements, and similarly, the join of any two elements is the least common multiple. And then here on the right, I have just a little stranger example of a lattice, just to show you that there's some kind of little bit nastier looking pictures that can be lattices. Okay, so what is the lattice problem? The lattice problem is to design a space-efficient data structure over a lattice supporting the following operations. You want to be able to test order, which is to return if x is less than or equal to y, and you want to be able to compute meets, which is to return the meet of x and y, and joins, return the join of x and y. All these elements are elements of the lattice. So there is a lower bound on any data structure for the lattice problem, and that is, since there are 2 to the theta n root n lattices on n elements, any lattice data structure must take at least a log number of bits of the possible number of elements, and so that means that any lattice data structure must take n root n bits. Okay, so what is the previous work on the lattice problem? There's kind of two naive approaches that seem to almost suggest themselves. The first idea is that we can just store a quadratic amount of information in the lattice, and since everything is just stored beforehand, we can compute order testing and meets and joins in constant time. Then there's another approach, which reduces the space usage at the cost of time, and that is we can store what's called the transitive reduction graph. And basically this, if we go back to our examples, the transitive reduction graph is just, it's the smallest number of relations such that all the transitive relations can be inferred. So I don't need to store the relation between 15 and 60. We know 15 divides 60 because 15 divides 30 and 30 divides 60. So if I store just these what's called the transitive reduction graph, this graph ends up having n root n edges, also called covering relations. And so I can store this in n root n words of space, but order testing and meets and joins are going to take at least linear time. All right, so the first data structure for the lattice problem came out of practical applications, actually in programming languages. This is actually pretty important publication. It's got several hundred citations, but this data structure is heuristic, and it uses omega n squared space in the worst case. So it's not quite satisfying for a theoretician. We're trying to have worst case guarantees. Okay, so there were a series of papers in the 90s by Talamo and Voca, culminating in this SciComp paper of 99. And they have a data structure that they claim uses n root n words of space, does order testing in constant time, and can compute meets and joins in square root n time. Unfortunately, there is a critical error in actually all 3 of the papers they published on this on the lattice data structure, and so it does not appear yeah, so these papers are not correct, and in particular, we don't see how to achieve the square root and meet and join complexities. Now, there's also been some tangential work by my two co-authors on distributive lattices. And this was in SOTA of a couple years ago. And they have a data structure that uses n log n bits of space and can compute meets and joins in log n time, where this is only if the lattice is distributive. Clearly, so this space bound is below our lower bound for general lattices. However, for distributive lattices, the space lower bound is all of n bits. So this is nearly optimal. Just real quick, distributive lattices. This lattice here on the left looks very nice, is in fact a distributive lattice. Some of the more uglier looking examples, like this one, are not distributive. So they have distributive lattices have a lot more structure. Okay, so what are our results? So we have basically three data structures, and our first data structure uses n root n words of space, can do order testing in constant time, and it can compute meets and joins in n to the 3/4 time. And actually, this data structure can be generalized to support a time-space trade-off, which interpolates directly between our space-efficient data structure and the naive attempt 1 to store quadratic amounts of information and compute meet and join in constant time. Okay, and then we also have a third data structure with complexity parameterized on the maximum degree in the transitive reduction graph of a lattice. This one also uses n root n words of space, and it can compute meets and joins in d log n over log d time. It's roughly linear in d. And this data structure ends up being much more efficient if this maximum degree is below n to the 3/4. Okay, we're going to focus on just this first data structure for this talk. And if you're interested in any of these two data structures or in things like the preprocessing costs or more about the Talamo-Avoca papers, we suggest that you read our paper. Okay, and from this point, we are going to refer to space complexity in words, just to make things simpler. Okay, so what is the intuition behind our data structure? So we're going to take this lattice and we're going to break it into smaller blocks, and we're going to store information within a block and between the block and the rest of the lattice. This is kind of a common technique used in data structure design, is to break down a problem and store pieces in blocks. Okay, so our goal is going to be to get square root n blocks of about square root n elements each. So why do we want this kind of square root decomposition? Well, our lower bound says that we need to use n root n bits of space, and there's some very nice things we can do if our decomposition is of this form. For example, within a block, since it has square root n elements, we can store a quadratic amount of information. And since there's only square root n blocks, quadratic and square root n, this becomes linear times root n. We get n root n space. And similarly, we can also store this information of between a block and the rest of the lattice. Since there's only square root n blocks, we can go ahead and use a whole linear amount of space per block to store this. So that would make things very nice. Unfortunately, we won't be able to arrive at this decomposition exactly. Okay, so how are we actually going to form our blocks? Well, we're going to do so in some sense the most natural way, which is that we'll just take some element, h, and then find all elements below h, and that will be our block. How will we choose h? I'm going to choose h so that the downside of h, all elements below h, is the smallest possible while satisfying the downside of h being at least size square root n. So what is this going to do? Well, this implies that any other element that's not the block header in the block is going to have a downset within the block of at most size square root n. That's because h is the largest, the smallest one above size square root n. Everything else must then be below size square root n in terms of the size of their downsets. Okay. Now we will go ahead and recurse. So we'll remove the initial block that we formed, and then we will update the sizes of all the downsets and use this to form m blocks with at least square root n elements, and then a residual block that might have a little bit less than square root n elements. Well, get a lot less, actually. But anyway, the implication then is that there are root n blocks, which is something we wanted out of our intuition. Okay, we're now ready to discuss the information needed to compute order testing. Okay, so for each element x, we're going to store the meat of x with all the different block headers. And then for an element x, we'll also store the intersection of its downset with the block in which it resides. So you can see here, just for all elements x, we'll store all these meats. And then within a block, we just store the downsets. They might intersect for two different elements. We'll just store everything. What's the space complexity? So implication 2 says that we have the most square root n blocks. And so that means we can go ahead and store all this information in A and root n words of space. And now for data structure B, we also know that for any element that isn't a block header, by implication 1, this downset is at most, well, the intersection of the downset with a block has size at most square root n. So that's how we get n root n overall, except we also need to think of the block headers. Well, it actually is possible that a particular block could be quite large. Particular block could be as big as a linear size. However, the blocks form a partition, and therefore the overall space usage across all the block headers in terms of storing them in a dictionary is going to be linear. Okay, so we're now ready to describe order testing. Okay, so suppose x is in block bi. We will then compute y meet hi, and we're going to report yes if and only if x is in the downset of y meted with hi intersecting with bi. Okay, so this picture here depicts what's going on. So we know that x is below hi because x is in bi. Then to determine if x is below y, well, all elements that are below both y and hi must be below y meet hi by the definition of a lattice. So I can just determine if x is below y by just determining if x is in the downset of y meet hi, which is some element in bi. Okay, so what's the time complexity of order testing? By our data structure A, we have all the meets of every element with every block header stored. Therefore, that could be computed in constant time without a single lookup. And similarly, we have the downsets of every element intersected with the block in which it resides, also stored in a dictionary, so we can determine if x is in this set in constant time. Okay, we're now ready to discuss the meet and join algorithms. So we're going to go ahead and focus on meet, and the reasoning is that these meet and join algorithms, the meet and join operations are dual. So if I can compute meets in the original lattice, I can actually flip partial order around, turn all the less thans into greater thans, and if I build the data structure on the flipped partial order, it will actually compute joins in the original lattice. So I just need to be able to compute either meets or joins, and I get the other one for free. Okay, so the first observation, well, I guess the first idea is we already have this block decomposition for the order testing. It seemed to work pretty well. Why don't we go ahead and try to use it again for the meet algorithm? Well, if we do so, the first kind of an unfortunate thing is that it does appear that the meet of x, and y can be in really any block, and it's really not clear which one it's going to be. So it does appear that we might have to just check every block. Okay, well, let's just suppose for a moment that x meet y is in block bi, and we know this. Then actually get this beautiful identity, which is that x meet y is equal to x meet hi meted with y meet hi. All right, so why is this true? The picture tells all. We see here, if I have x has got its downset here. So we know, this is very similar to the order testing, but so x meet y is in bi, which implies that it must be below hi. So again, any element that is below both x and hi is going to be below x meet hi. You can say the same thing about y and hi, must be below y meet hi. And then similarly, any element that is below both x and y is now going to be below both x meet hi and y meet hi, which then gets you x meet hi meet y meet hi. This is element that must be below, and so we see this identity must hold. Okay, we're now ready to discuss the meet algorithm. Okay, so the first step is that we will compute x meet hi for all hi, and we'll compute y meet hi for all hi. And I've depicted this in the picture here to the right. All these blue dots are the meets of x with the block headers, and the red dots are the meets of y with the block headers. Okay, then we'll go ahead and compute this element zi as described in the previous slide, which is the meet of x meet hi and y meet hi for each of the respective blocks I. So let's go ahead and just kind of go through this with the different blocks. So if we look at block bi, the meet of hi and x is this blue dot here, and the meet of y with hi is actually hi itself. If you look at the meet of these two elements, it's going to just be the lower one since this element is below h1. And then similarly, I can do this for block b2. We got these two elements are the meets of x and y with the block header, which we get this z2 is going to be here. And similarly for block b3, we got x meet h3, y meet h3, and this is going to fall right here on z3. All right, finally, we do have this block b4, and actually the meet of y with b4 doesn't fall within the block b4, and so we can go ahead and just disregard this because then clearly the meet of x and y is not going to be in block b4. Okay, we do have just one bit of a special case. This will be more important actually later on, but let's go ahead and discuss it now, and that is if both x and y are in this residual block, we're going to go ahead and find the, we're going to find intersections of the downsets of x and y in the residual block manually. So I've got the downsets of x and y with the residual block depicted here in green. However, their intersection is actually empty. So for this particular example, we will get no candidate meets from step 3. Okay, but now we have this set of candidate meets from steps 2 and 3. And by the previous slide, we know that the true meet must be one of these candidate meets. But which one? Well, it turns out it must be the largest element. So why is this the case? Well, let's look. For all of these zi's, we know that the element zi must be below both x and y. Why is this? Well, if you take x and meet it with something, keep meeting it, you're going to just stay within the downset of x. So clearly, this zi's, everything found in step 2 must be below both x and y. Similarly, in step 3, it's pretty clear everything is going to be below both x and y. And then if it's below, if the elements are below x and y, and the true meet is part of the set, then we know by the definition of a lattice, all these other elements must be below the true meet. Therefore, the true meet must be the largest element. Okay, let's analyze the time complexity. So for step 1, by implication 2, there are most square root n blocks, and I have all of the meets stored. So this is going to take square root n time. Let's go ahead and skip step 2 for the moment. Now step 3, by implication 1, the intersection of these downsets with the residual block are both size square root n, and we have them stored in a dictionary in this data structure B. Therefore, we can determine this intersection in time proportional to the smaller set, which is going to be square root n. Now, the number of elements returned in steps 2 and 3 is at most square root n. Therefore, we can use the order testing data structure to find the largest element, also in square root n time. All right, so what about the step 2? Well, actually, if you look at what we're computing here, we're actually computing a meet of 2 elements within a block, right? We got like x meet h3 and y meet h3. We need to determine their meets. They're both in B3. Well, we can recurse to do this efficiently. We can subdivide each block bi into subblocks, including a residual subblock. So if we do this, what size should we choose for the subblocks? Well, the square root n seem to work pretty well at the top level. Why don't we go ahead and use square root in the size of the block at the subblock level? And then to stop this recursion from happening too long, we'll just keep it to 2 levels. We'll just go ahead and store the meets of all pairs of elements in each subblock. Except for the residual subblocks, we won't store the meets for those. Okay, what is the space complexity? So the recursion, this is just data structures A and B on the lower level. Well, data structures A and B take time, use space n root n. Adjusted for the block size, it's going to be the size of the block to the 1.5. This is the most n root n overall. You sum over all the blocks. Now let's consider this new data structure C. So we're storing a quadratic amount of information in the size of the subblock. However, let's look at the sizes of these subblocks. They're all downsets of elements that are below a block header on the top level. That means by implication 1, these downsets are of size at most square root n. Therefore, if we go back to our intuition, we can go ahead and actually store a quadratic amount of information. And this is going to end up being n root n overall. Okay, great. So let's now analyze this time complexity for the total meet algorithm. We now have 2 levels. Let's try to figure it out. So I've gone ahead and adjusted the picture for the subblock level as well as the algorithm. And let's see what happens. So actually, steps 1, 3, and 4 follow similarly to how they did at the top level, and they get square root of the size of the block. Now for step 2, I can actually go ahead and just look it up in this table C, because this is a meet of 2 elements in a subblock. I've stored all of these. And now, real quick here, I will mention that this step 3 now becomes important. I did not store the meets of any elements in any pairs of elements in the residual subblock. And that's because this residual subblock can be quite large. However, we do know that x and y, their downsets intersected with the residual subblock must be of size square root bi. So the complexity still carries through and works out so that we have meet in block bi with time square root bi. Okay, let's go ahead and adjust this algorithm back to the top level and pull the analysis back. Steps 1, 3, and 4 follow as described previously. And then we can go ahead and plug in this square root in the size of the block into our complexity for step 2. And what does this come out to? It comes out to n to the 3/4 time by a pretty nice application of actually Jensen's inequality. This quantity is maximized when the sizes of the blocks are the same. It's going to come out to being at most n to the 3/4 time overall. And that's going to be it. Thank you so much.